In order to better understand the goal of static balancing rotor blades on the universal static balance fixture, hereafter referred to as the USBF, let's compare this process by observing big man and little man on a teeter-totter. Let's put big man on one side and little man on the other. As seen in this illustration, because big man is much heavier than the little man, they definitely have a balance problem. It's clear that to balance, the big man will have to move closer to the balance fulcrum. When they are in this level balance position, you will find that little man's weight times little man's distance to the fulcrum is equal to the big man's weight times the big man's distance from the fulcrum. The torque on the teeter-totter created in one direction by the little man is equal to the torque created in the other direction by the big man. You will recall that in weight and balance calculations, a weight times a distance is called a moment. When the little man's moment counterclockwise is equal to the big man's moment clockwise, they are in static balance. The same mathematical principle holds for static balance of rotor blades. The USBF accomplishes a 3-point weight and balance calculation on a blade and provides the computer algorithm the weight and distance from the mast or fulcrum to the blade's center of gravity. The computer multiplies the weight times this distance and produces a span moment. When the span moments on opposing blades are equal, the two blades are in static balance. When the span moments are equal to the master blade or drawing span moment, the blades become interchangeable. A rotor blade weighing 300 pounds on one side and 303 pounds on the other side may be in static balance if the center of gravity of the heavier blade is closer to the root end of the blade. The objective of the USBF is to produce span moments equal to the master blade requirement and therefore producing interchangeable rotor blades. What really counts is after installing rotor blades on an aircraft hub, you have weights available to dynamically balance. Static balancing takes different weight blades and makes them fly together well enough that you are able to dynamically balance them with the hub. Dynamic balance minimizes vibration, thereby reducing the wear and tear on the airframe, dynamic components, and crew. Turn on the power switch, then flip the red toggle switch. It's a two-step process to turn on the computer. Since this is a universal static balance fixture, the machine has to be set up to accept the type of blade to be balanced. Today we are going to balance a Chinook rotor blade, so we have to make sure the machine is set up to balance this blade. First, at the main menu, select Blade. Then select the blade type to be balanced. In this instance, we select the Chinook forward blade button, which sets up the machine with the correct software for the Chinook forward blade. The selected blade is then indicated on the top of the main menu screen, as shown here. Next, we have to check the USBF to make sure it has the correct mechanical setup for this blade. You can read the operator's manual for instructions or follow the setup details on the various decals affixed to the machine. If you look on the side of the sensor blocks, you have 3 positions to choose from for the position pin: CH47, AH64, AH1/UH60, and UH1. The same choices are on the second sensor block. On the side, there is a decal which indicates the type of feet you need on the teeter-totter: 1 nut, 2 nut, and 3 nut feet. The graphic indicates where to place the type of feet on the teeter-totter. At the end of the fixture, you see a similar decal which display the graphics for the crossbar with 5 positions, showing you where to place feet on the crossbar for each blade type. The leading edge of the blade is always facing toward the position pin. Chinook rotor blades have both a forward and an aft rotor blade. For a forward rotor blade, the load bar comes off. Pull the pin out of the load cell bar and turn the whole load cell bar around. Undo the crossbar and turn the crossbar around so the leading edge is always at the pin. On some rotor blades, we take the whole load cell bar out and move it up to a different location and mate it up with the crossbar moved to the same station. This location is for blade types AH1, AH64, and OH58. The program knows what the approximate load for the blade type is supposed to be on each load cell. If the crossbar or load cell bar is in the wrong station location for the blade type to be balanced, or if the setup is wrong, the software will ask you if you have the machine set up correctly or if you are balancing the type of blade that was selected. If it is set up correctly and the correct blade type software is indicated, go ahead and run the program. The blade is probably way out of tolerance because of water, excessive paint, or poor repairs. We have set up the machine to balance a Chinook forward rotor blade. The blade is not loaded, but is ready to be loaded and the right software is selected. Select Balance. This is a new balance for the day, so we will select New and enter the operator's name. Enter the blade serial number. This data is being saved to the database in the computer. The computer asks you to push position sensor 1. Move the blade slightly out of position. Hold your fingers on the fixture and push the LVDT block all the way in with your thumbs and hold it for a couple of seconds. When you release the sensor back, the computer beeps to indicate it received the data. Do the same thing for position sensor 2. The machine is now doing a sensor calibration on the LVDTs. The LVDTs are used to find the rotor blade in relation to the load cells. Now we will load the blade. The Chinook has a pin that goes through the lag damper arm and into the dog ears to locate the blade spanwise. Using the blade lift dolly, set the blade down and pull up towards the 2 position pins. The blade has to be within 3/8 inches of the position pins and not touching. Carefully lower the blade with the blade lift dolly. After the blade is placed, make sure it is not touching the cart and that the cart is not touching the load bar. Once the blade is loaded, select OK. Remove the index pin because you do not want to weigh the index pin as part of the blade. The machine will then require you to push position sensor 1 and hold against the blade for a second. Then you will be requested to push position sensor 2 and hold for a second. We set the blade down approximately where it needs to be in relation to the load cells, and then go locate it precisely. With this correction data indexing, the program can calculate the center of gravity, span, and chord moments. The computer will then collect the load data. The display will now prompt you to provide inventory. There are 10 Vibrex plates out on the tip. The software is asking you to count the plates on the end of the blade. On a Chinook, the USBF will attempt to have you install 10 Vibrex plates. Sometimes the solution only has you load 9. After inputting inventory, the program runs a completion, and the results are presented on the screen. The software may ask you, do you want to rebalance? If not, select No. Enter comments if desired, and select Cancel to return to the main menu. If you answer yes, the USBF can reweight the blade without going through the reloading of the blade steps. This can be very useful when the program is asking the user to add weights. Simply locate the recommended weights on top of the blade at the station position where they would be when installed. Then answer yes. With care and weight placement, after this rebalance run, the program will return a Good blade report. Install the weights, and you are finished. For other blade types, such as the UH60 and AH64, when the operator is asked to load the blade, a cam pin is inserted into the forward vertical pinhole at the root end. When asked to load the blade, the operator loads the blade with the index pin pulled against the index fence, as shown here. The software will require the operator to push continue, and then will require the operator to turn the index pin until the cam contacts the index fence. Reading the scale on the pin and typing the number into the program will be required. The program then proceeds as it did for the Chinook blade. Pushing the print button on the screen will provide a hard copy of the screen display to use for reference when the technicians make the weight changes. Now let's take a look at other menu items available from the main menu. We've already talked about blade type and balance. Let's select the Utilities menu. All of the blade data has been stored on the computer sequentially by blade serial number. If you don't know the blade serial number, you can select List Serial Numbers to list all of the serial numbers in the database. Last results is used quite often. Choose your blade type and enter the blade serial number. If the last balance results were saved to the database, it would display the last record, which can then be printed using the print selections so the mechanics can use the results to work on the rotor blade. All results will give you all of the historical results for a particular rotor blade serial number. For example, A2:1234. All records for A2:1234 will be printed to the screen in the order that they were saved to the computer. This blade may have 5 records, and reviewing the history may provide an insight into what is going on with a blade. Is it getting heavier over time and gaining weight, for instance? If something happens to the software and an Avion technician needs to send the unit fixed files, the technician can use Copy System Files to your system using this function. If the technician needs your historical data, you can extract historical data for use in troubleshooting, for statistics data, or if you need it at your location. We can show you how to convert it if requested. Your .ini file may change. For example, if you have a new computer serial number or new load cells which are unique to this machine and this computer's software. If you receive a new load cell, you will get a new curve for that load cell, and we can update your software using install new .ini file. Going back to the main menu. Now, let us select the Setup menu. Under the Setup menu, we see Calibration Check. Let's provide some background before we make this menu selection. There is only one way to calibrate a load cell according to the experts, by putting a known weight on the load cell and measuring it. Even though the program automatically does a resistance calibration check before every run, the calibration experts still want a periodic known weight check to assure quality. We have a calibration check which instructs you to remove the load bar and remove all of the feet from the load bar because they vary in size and weight, for example, 1, 2, or 3 nut feet. The calibration check will evaluate the load bar as if it is a rotor blade. It will perform the system calibration check up front, zero the scale, and then tell you to load the load bar. The program will evaluate the load bar's weight and span moments against what is in the system software for that set of load cells in this computer and this load bar. If you are in tolerance, the software will reflect a pass message and write this to the database with the current data included. If you are out of tolerance, the software will inform you to contact an Avion technician. Location. Most units put their unit designation here. Once you have entered this data, all reports will reflect this data without the need to re-enter. Gravity. These settings are required for your fixture to function at your current location. Under Gravity, we have 2 submenus. Latitude. You can take this machine to different locations around the world. Latitude is required because electronic scales measure gravity differently depending on your location. Centrifugal force at the equator is pushing you out because of the rotation of the Earth, so your weight is less there than at the poles where there is no centrifugal force and you have true weight. You can get this data for your location off of instrument approach charts from a pilot or off the internet. Elevation. Much like latitude, elevation will also affect the USBF. You can get this data by checking instrument approach charts or by researching online. For more information, you can check the Help section on the main menu or refer to your user's manual.